Mehta. So today we will see the implementation of the hex CPU. Let's begin. So what is a hex CPU? The hex CPU is based on von Neumann architecture and it comprises of central processing unit that receives the instruction from the memory and executes it. So to understand the implementation of the hex CPU, first we need to go through the diagram. This is a diagram of the hex CPU. It is very important to understand it to understand the syntax of the code of the hex CPU. Here is our instruction binary syntax instruction. So it is also very important while we'll go through the syntax or the code of the Hague machine language. So let's begin with the code. So in chip CPU there is an instruction mpin. So it is used to assess the memory location at the address A register of the RAM A. Second is our instruction. So this instruction is used to receive the instruction in the CPU. It is a 16-bit instruction pin and this is also a 16-bit input pin. So this is a reset pin, so it helps in resetting the CPU. There are 4 output pins. First is our out M, which is 16-bit output pin of the it controls the 16-bit output of the operations performed by the ALU. So second is our write M. If the output is 1, then it will update the M register, and if the output is 0, then it will not update and the value will be remains same. Next is our address M, which is a 15-bit output pin. It specifies M register of the RAM. Next and last output pin is PC. It is also a 15-bit output pin, and it specifies the 15-bit address to be of the next instruction to be fetched. Let's come to the parts. So first is our note chip. If it indicates output is A instruction or C instruction, and second also does the same work. It also indicates that the output is A instruction or C instruction. If the output is 0, then it means it is a C instruction, and if the output is 1, then it means it is a A instruction. So we can understand it better in this diagram. So this is our opcode, and if the opcode is 0, then it is a C instruction, and if the opcode is 1, then it is a instruction. That's why I said that it is also necessary to understand this instruction. Next is our AND gate. This AND gate helps in the selection of the ALU output, and this is our mux chip. It is 16-bit mux chip. So if the selection pin is 1, then it will send the ALU output, and if the it is 0, then it will pass the instruction. Next is our OR gate. It helps in the load of A register, and A register is a built-in chip. So this when if it is 1, if the load is 1, then it will update the value of the A register, and if the value is load is 0, then it will remain same. Next is our mux chip. So here our instruction 12 is fetched into the selection, and if the instruction 12 is 1, then it will give the output of in M, and if it is 0, then it will give A out. We can understand it better through this diagram. So this is our 12th instruction. So if it is 1, then it will give the output of this no, if it is 1, then it will give output of this ALU out, and if it is 0, then it will give the output of instruction out A out, sorry. So next is our AND. So this in this this AND helps in the loading of the D register. So here again D register is our built-in chip. If the load in it is 1, then it will give update its value, or if it is not 1 or 0, then it will remain same, the value in the D register remains same. Next is our ALU chip, which we have done earlier also. So it have 2 input pins, 6 output pins, and 6 instruction pins and 3 output pins. So here 2 input pins are fetched, 6 instruction pins 11, 10, 9, 8, 7 and 6, which we can see in this diagram. So these 6 instruction pins are these: C1, C2, C3, C4, C5 and C6, and output pins are ALU out, ZR out and NG out. Next is our OR16 gate. It sets output pin to A out, and opcode will be 0 as A instruction opcode is 0. As we know that if it is A instruction, then opcode is 0. This is our OR gate, and it also sets the output to the ALU out. Next is our AND gate. So it controls what's in the M register, and instruction 3 is selected. uh, and it will update the value of the memory register what is needed to be write in it. Next is our AND gate. So this AND gate start executing if the Z are out and instruction 1 are equal, and this AND gate also starts executing if the NG out is less than instruction. Next is our OR gate, which indicates that our output is 0 or negative. Next is our NOR gate, which will reverse the value of this previous OR gate and indicate that it is positive. And this will also be used in next AND gate, and this AND gate it will in this AND gate it will control the jump greater than instruction. Uh, so we have a total of 8 jump instructions, and these last three jump bits controls the jump all these jump instructions. Next is our OR gate, which will load the jump equal and less than and help in execution of jump less than equal to instruction. Next is our OR gate, which will load jump less than equal to and greater than instruction, and helps in controlling uh, jump to A, that if it needs to jump to A or not. Next is our instruction and gate, so it will help to load the PC. Next is our NOT gate, which will negate the PC and output, which is PC load, which will be fetched as the instruction pin in PC. Last is our PC, which is used to send the address of the next instruction which is needed to be fetched. This is all about our the hack CPU implementation. Thank you.